All right. So um, today we're going to learn about exponential functions. It is the uh, third. It is the second function that we're going to be learning during the course of the year. What is unique about the exponential function is that it is our first non-linear function. Okay, so that means when you graph it, it is not a straight line. Okay. Um, uh, when it comes to exponential functions, there is really only one form that we're going to see here. There's also just one way we graph it. It is a lot easier than linear functions, right? Linear functions, we had point slope form, we had standard form where we covered up, did the cover up method, and then slope intercept form. And there were different methods to use to graph those. But here, with exponential functions, we will use one method for every type. Okay. So this is our standard form of an exponential function. It's got a lot of different pieces that we're going to kind of define. And then in this lesson, we're not doing any story problems. We'll save those for Monday. Um, and so we're just going to look to see what these graphs look like, and then work through a couple of different scenarios. So the exponential function, we will notice that the input, what we plug into the function, is in the exponent. Hence the name, an exponential function. Okay. So f of x equals a times b raised to the x plus k. So let's talk about what each of these pieces actually mean. Let's start with, we're just going to work from kind of from left to right. Let's start with f of x. We should know that f of x, when we think about function notation, is the output value. Is the output value. What is another name for output? We talked about this. We probably haven't talked about this since chapter 1. Maybe a little bit with linear functions. Starts with an R.
Range.
Yes, range. So if f of x is the output or the range, what is the x value? What would we call the x? If f of x is the output, input, okay, because that's what we plug into the function. And then what's the corresponding word with range? Domain. With functions from that we see the rest of the year, the domain and the range, they change. With a linear function, it's all real numbers. You can plug anything in, you can get anything out. B is a unique piece to exponential functions. This is the growth or decay factor. Okay. Who has heard of exponential growth? Like in science class, like bacteria growing, or something like that. What about exponential decay? Also science class. Cool. So those are exponential functions. But how do we tell if something is growing or if something is decaying? It is exponential growth when the b is bigger than 1. Okay? Think about inflation would be a great example of that. Okay? When b is positive, when b is bigger than 1, the values are growing. They're getting bigger. If it is decaying, It is between 0 and 1. Okay. So a good example of this is like if something is on sale, right? If we say a $10 shirt is 80% off, that would be an example of like exponential decay because you're only paying for, I said 80%. So you're only paying for 20% of the actual value. Okay. Now let's talk about the y-intercept. For any function, what is the value of x at the y-intercept?
0.
0. So when x is 0, y is going to equal a particular expression. Let's think about this as we look at this function. If I plug 0 into x, I have a times b raised to the 0 plus k. What is anything raised to the 0?
1.
So this expression turns into a plus k, regardless of whether a is positive or negative, regardless whether k is positive or negative. We will put a plus k. Now, k is a unique feature to this graph. K is called a it is a horizontal asymptote. An asymptote is a line. It could be horizontal like this. There are other types of asymptotes that are beyond this class. An asymptote is an imaginary line in the graph that the function approaches. So like in our graphs today, we will draw a horizontal asymptote with each of our graphs. Okay. Right. Now, we do also talk about there being like an equation when it comes to the horizontal asymptote. Since it's a horizontal line, we'll write them as y equals k. So it's whatever that number is on the outside. Okay, so it's this boundary line that the graph does not cross. Yep. All right. All right. Now, before we get into our examples, let's just talk about a little bit of what exponential growth and exponential decay look like. So let's first talk about growth. When we talk about exponential growth, we're talking about that value for b is bigger than 1. When we look at exponential growth graphs, they are going to look like this most of the time. Okay. The values are growing exponentially. Exponential functions are based on multiplying because when we think about the exponents, if I have like 2 raised to the x, I'm doing 2 times 2 times 2 times 2 times 2 times 2 x number of times. Decay where b is between 0 and 1, it flips. So it looks like that. Okay, it's decaying. The values are getting smaller. Okay. Now, what is important to recognize here as well is that it has to be a special scenario for there to be negative values. Okay. All right. So there are 4 things that are going to be important for us to remember as we think about graphing exponential functions. We've talked about the properties. Now let's talk about how to actually graph it. Number one, we have to remember it is nonlinear. So none of our graphs should we have straight lines connecting the dots. Number two, you will plug in these same three values every single time. -1, 0, and +1. There is no rate of change that we are using. Oh,
fries.
Fries.
I probably like touched something on the board. There's no rate of change that we are using from the function to go from one point to the next. Okay. We will always plug in -1, 0, and +1. These graphs, because we're going to use a table, I feel like these graphs are even easier to do than linear functions, because we're just calculating points. The domain will always be all real numbers. Okay. We can plug anything into these functions. It won't be until Algebra 2 where that actually catches. And then the range. The range will depend on a few different things. We will either have y is bigger than k or y is less than k. That horizontal asymptote at k, it cannot be crossed. Okay, so it's either going to be bigger than k or less than k. How do we know which one it is? It will be bigger than k if a is positive. So if that number in the front is positive, it'll be bigger than k. And then the opposite will be true for less than k. So hopefully in the rest of our time today, we're gonna work through 5 of these graphs. Okay. We are out of here at 1:30, so 17 minutes. We can do it. All right, so here's our example. We're going to graph each function, determine the y-intercept, determine the domain, determine the range, and the horizontal asymptote. So, step 1. I make my table. So, 2 times 4 raised to the -1. Oh, that is 2 divided by 4, which is 1/2. Because remember that negative exponent, that becomes 2 over 4, which is 1/2. 2 times 4 raised to the 0. What's 4 to the 0?
1.
What's 2 times 1?
2.
What's 2 times 4 raised to the first?
8.
Notice when I go from 1/2 to 2 to 8, I'm multiplying by 4. That will happen every single time. All right, so let's plot these points. -1, 1/2, 0, 2, 1, 8. Okay. My domain is all real numbers. My range is y is bigger than 0. Is bigger than 0 because on this 2 times 4 raised to the x is a plus 0 on the outside for that value for k. So I have a horizontal asymptote right here. Y equals 0. Okay. It's a dashed line. It's a little boundary that the graph does not cross. Here's my y-intercept at 0, 2. Now I connect the dots. We will do that for every single problem. Okay. So we make the table. The domain is all real numbers, always. The range connects to that horizontal asymptote, which in this case is 0. I draw that in and I connect the dots. B. 4 times 1/2. Oh, here's one thing I forgot to say for that first one. 2 times 4 raised to the x. I'll put this in red. This is not 8. This is not 8 to the x. You cannot combine these because they are not the same base. Okay. You will never combine those. Okay. That's your public service announcement for today. Tally ho. All right. X, h of x. -1, 0, +1. And I'm totally fine if you use your calculators to calculate these. 4 times 1/2 raised to the -1. That becomes 4 times 2, which is 8 plus 1 is 9. -1, 9. Plug in 0. 4 times 1 plus 1 is 5. 0, 5. 4 times 1/2 is 2. 2 plus 1 is 3. I have a horizontal asymptote at 1. It's the only times that like the multiplying by 1/2 will appear is like if you don't have that plus or minus value on the outside. Okay. So my asymptote is right here. Y equals 1. Connect the dots. So domain, all real numbers. 0, 5 is my y-intercept. You can also point that out in the table. So then for this one, what is my range going to be? What's my range? If I look at the graph. Give me the first part. Will it be y is bigger than 1 or y is less than 1? Great. Because 1 is the smallest value that it can reach. But like it can't touch it. Graph, domain range.